All right, so today we're looking at the laws of limits, how to evaluate limits effectively using their properties. This can be a tricky place just because it does rely on some algebra, it relies on knowing what the domains of functions are, and those things can be a little rusty at this point. But we're going to walk through it step by step, and you should be set up for success. Now I'm going to write down these properties of limits and we'll use them to evaluate them. Again, the goal of these is to make life simpler, not harder. And for these, since we're not really covering the formal definition of a limit in full here in this course, you're going to kind of have to take it on faith that these just line up with what you know and what I've told you so far. Okay? So I'll write these down and then we'll go through them together. Okay, so the first thing first, we have to define what we're talking about. So we say A, this notation means that A is an element of the real numbers. Okay, or A is in the real numbers. It's a math way of saying that. It's constant, and we know that the limit of f and the limit of g exist at A. These are assumptions that we're going to make for these problems, okay? So then the properties are as such. Let me pull these down here a little bit. And the properties are these. The first one is what we call the sum property, which says if you have the limit of two functions inside that are being added, you can split that up into a sum of two limits. Okay, so you can break it over a sum. For a couple of these, maybe I'll give you a real example. So this means, like the limit as x approaches 2 of x squared plus 3x. We could say that this is the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3x. Okay. Same is true for subtraction, so no need to really explain that much further. This one here, that if you have some constant times a function inside that, you can pull that constant outside of the limit. So for example, if I had the limit as x approaches 2 of 3x, let's use that one of the limits from up there. This is the same as 3 times the limit as x approaches 2 of x. Okay? So you can pull a scalar outside of the limit. That's no problem. This one says that you can have the product of two functions inside and split that up into a product of the limits of f times g. All right, and what that, an example of that would be, let's say the limit as x approaches pi of sine x cos x. This is really the limit as x approaches pi of sine x times the limit as x approaches pi of cos x. Okay, so whatever product you have within there, you can split it into the product of the limits. Last one has to deal with quotients. If x is going to a, and you have a quotient here, this is the only one we need to be careful of. You can split this up. This is the limit as x goes to a of f over the limit as x goes to a of g. This is provided, though, if the limit as x approaches g, or as x approaches a of g is not 0. Okay, still can't divide by 0. All right, and so that should be self-explanatory. We also have the power law, which says that if you've got the limit as x approaches a of f of x to some nth power, this is the same as raising the whole limit to that power. Okay, so, this would be the same as saying, so if I had the limit as x approaches 3 of x to the 4th, I could really say, well, this is the same as taking the limit as x approaches 3 of x all to the fourth. Okay. And so, well, there's one more before I want to give you the good news. The last one is the rational law, rational power law, or root law. And that says that as the limit as x approaches a from some nth root of x, this is the nth root of the whole limit. Okay, so very similar to before. And so why these are nice is because we have these two additional properties that you're going to need. Which is that the limit as, getting a little sloppy with this here. I write these so many times that I just drop 2 out of the 3 letters. So as x approaches a of x, so if we just take the limit as x approaches a, what is this limit? So as what is x approaching as we approach a? Well, it's got to be approaching a. If it was something else, that would be very confusing, right? So a limit of x equals a as x approaches a. And the other is that the limit of some k as x approaches a, some constant, that's just k. All right, so what does this mean? It means if you have some constant, let's say k is 4, what is 4 approaching as x approaches a? Well, 4 doesn't care, right? 4 is just going to continue to be 4. So with these and with all the laws we've gone over so far, we can evaluate a lot of limits algebraically as long as we understand how to apply them. All right, so for a quick example, if we're given a polynomial here and we're asked to evaluate this limit as x approaches 4, again, we can break this up. We see that we have really three functions in here that are being broken up by addition and subtraction. So really this is equal to the limit as x approaches 4 of 3x squared minus the limit as x approaches 4 of 2x plus the limit as x approaches 4 of 4. Okay, so I can split up the limits over, excuse me, addition and subtraction. From there, I can use the fact that scalars can be pulled out. So here's a scalar next to x. Here's a scalar next to x. This is a constant, so there's nothing to do here. This is really 3 times the limit as x approaches 4 of x squared minus 2 times the limit as x approaches 4 of x, and then plus the limit as x approaches 4 of 4. And so from here, we could be extra thorough here and say in here, we can change this to be the power of the limit, right? The limit of x squared is the same as squaring the limit of x. And so this becomes 3 times the limit as x approaches 4 of x squared minus 2 times the limit as x approaches 4 of x plus the limit of 4 as x approaches 4. And so now we're down to a place where we can use those last two properties on all these limits and evaluate them. We know the limit. What is x going to as x goes to 4? It's going to 4. Same here. This is going to 4. And this last one's going to 4, but just because the constant is 4, right? So this is also going to 4. But then we have these other pieces. So this is 3 times 4 squared minus 2 times 4 plus 4. So make sure you can pause here and make sure that all makes sense before moving on. From here, it's just evaluating. So 3 times 4 squared, that's 3 times 16 is 48, minus 8 plus 4, which is a grand total of 44. Now, you're going to apply these rules in this way a few times to demonstrate to yourself how these work and how you can always break it down like this. But eventually, you can come to the understanding that all polynomials, p of x, or rational functions, functions q of x are, or let's say have the property that the limit of p of x as x approaches any a is equal to p of a as long as a is in the domain. So as long as it doesn't blow up the function, the limit of a polynomial or rational function is always going to be able to, you're always going to be able to do this. So in other words, we could have just said, this is the limit, or not, we can lose the limit notation. We could say, all right, this is really the same as, if this is my p of x, this is really the same as p of 4, since it's all a polynomial, which is just 3 times 4 squared minus 2 times 4 plus 4, right, which gets us to our end result. You can't always do that with every single function, but with polynomials you can, because of how this will always go. Okay, but again, you need to practice with this before just relying on that, because then you'll see why it breaks down for other functions. Okay, another key factor you're going to need is that if two functions are equal except at a single point, when x is not equal to a, if they're equal everywhere else, then their limits are going to equal each other at x equals a. So what that means is, if one function maybe isn't defined at one single point, and the other one is, and they're equal everywhere else, then those limits are the same. Okay, and that's provided that they exist. So one way that we use this in practice is that we can often use algebra to kind of get around something that might be a problem. So we take a look at this limit here. The limit as h goes to 0, from just looking at this from the outside, you'd see that this is going to 0 in the denominator and this is going to blow up. Okay, that's a problem. However, if we massage this a little bit using some algebra, we distribute the terms in the top. We'll get 16 plus what? 8h plus h squared minus 16 all over h. We see the 16s cancel. We're left with the limit as h goes to 0 of 8h plus h squared all over h. We use this property in the following way. We say, well, even though h is a problem here, if I factor out an h in the top, since we're really only considering during the limit the values where h is not 0, right? Remember, we're not talking about actually being at 0. We're talking about approaching 0. So then, since we're not actually going to h equals 0, we're not actually using that value, we can use the equivalent function, some g of x, where it doesn't have this issue, because I can cancel this common factor of h, and so I'll be left with the limit, an equivalent limit, as h goes to 0, of just 8 plus h, which is then just 8. Right, so here we are able to get around what we call, this is a removable discontinuity. By using this fact. Now, this is not, right, it is not saying that 8 minus h is not the same as this function here. This one does have a problem at h equals 0. However, we used this property here that said, well, you know, it's equal everywhere else when x is not equal to a. So then that limit is going to exist when we do approach a with x. Okay, so make sure that this makes sense. Maybe run through that yourself. You'll have some time to practice this with some exercises as well. The next idea, we did cover it in the last section briefly, is that of one-sided limits. And what you need to know now a bit more officially is that we have this theorem that the limit for a function only exists, so we'd say it's equal to L, if and only if, meaning this is only the case if this is true, the limit of x as it approaches a from the left is equal to L, and that this also equals the limit, the one-sided limit, as we approach a from the right. Remember, we did this numerically and graphically last time. Okay, but this is going to be key and often a way that we'd be able to solve a problem. We see that the limit from the left and the right are the same or different, and that will tell us whether or not the limit really exists on its own. So an example of this, and it's possible we did this in the last video, that's how short my memory is these days. We can look at the limit as x approaches 3 of absolute value of x minus 3 over x minus 3. Look at that. We'll look at the one-sided limit. I'll go from the left first. Of this function x minus 3 absolute value over x minus 3. And then we'll also look at the right-hand limit. All right. So here, if we graph this function, this is what we see. This function has this jump discontinuity, we call it. Jump or step discontinuity. And so we'd say that the limit doesn't exist here because as we come at it from the left and come at it from the right, it doesn't agree. So we'd actually say that this limit does not exist. And the way that we can prove that, you can do this numerically too, or just plug in values and take a look, right? If I was plugging in from the left on this one-sided limit here, x equals 0 or something like this, you get 0 minus 3 in the absolute value over 0 minus 3 down here, right? And any one of these values that's less than 3 will do this. It'll cause you to get negative 1. And so the limit as you approach from the left is negative 1. And the limit as you approach from the right, think about 5 minus 3, 4 minus 3, 3.1 minus 3 in here, and you'll get positive 1 from the right-handed limit. So here we see this triple dot means therefore. Therefore, the limit from the right does not equal the limit from the left, so this implies that the limit does not exist. Okay. So sometimes we're used to the limit not existing because it blows up to infinity, but we can say that the limit doesn't exist when it just doesn't agree from either side. All right, so just to recap what we've done here, we looked at the basic properties of limits, how polynomials and rational functions, as long as the domain is, as long as the point is in the domain, that you can just evaluate these as is. Remembering that you can cancel out a removable discontinuity and still have an equivalent limit, even though the functions are different. If they got the same limit, they got the same limit, right? They're going to the same place. That's what that means. That's all limits really mean, is where it's approaching. And then this important theorem about one-sided limits. There is one more topic in this section called the squeeze theorem, and I'm probably going to cover this in a separate video. It's not a part of... It's not going to be necessarily on the final exam or anything like this, but it is a nice one to know for the future. So I might get to that, but this is all the properties you're going to need to tackle the exercises in this section before moving on.